Hello. In the last class, we are discussing about linear independence and spanning. We will quickly see an utilization of those ideas in context of solution of x is equal to b, because the entire course we are very focused in understanding how x is equal to b can be solved for certain cases. And at the beginning of this course, we have demonstrated that few direct solvers like Gauss elimination method, Gauss-Jordan technique, LU decomposition, TDMA, in which we can solve x is equal to b provided there is a unique solution of x is equal to b. A is a full rank matrix. Later we came to the case where A is not a full rank matrix and there are infinite or no solution of x is equal to b. We have seen that x is equal to 0 will always have a solution. X is equal to b will have a solution when b lies in the column space of A, and we tried to give definition of column space of A. X is equal to 0 will always have one solution, at least one solution. X is equal to 0 can have multiple solution if A is not a full rank matrix, and we also went through the exercise where we are finding multiple solutions of x is equal to 0, and we told that all these solutions will belong to null space. Now, we looked into linear independence, and we also looked at how different vectors in null space can be combined, and we can say that this is the spanning of these vectors span the null space, and we get a definition of the null space, description of the null space using the spanning vectors, which are obtained by getting reduced to echelon form of the A matrix and looking into the pivots, identifying the free variables, assigning one to one of the free variables and 0, and getting one of the null space vector, and that way for all free variables we got all null space vectors, and using those null space vectors we will allow the null space vectors to span over a space, and this space will be defined as null space. We have looked into this. So, we have also looked into column space, and the column space vectors are the vectors which lie in a space which is spanned by the columns of a particular matrix. Column space vector can be different than the column vector. Column vectors are given by the particular matrix. Now, if we think of a space spanned by the column vectors, any vector in that space will be a column space vector. So, of course, column vector is a column space vector, but there can be other column space vectors than column vector. We will look into existence and uniqueness of this of x is equal to b, and solution of solution x, when it will exist and when it will be unique, and we come to the definition of spanning and linear independence here. So, vector b must lie in the subspace spanned by the columns for the existence of solution. So, if solution b x is equal to b has to have a solution b which is existing, solution x which is existing, then b must be spanned by the columns of A. So, b should be, we should be able to write b as alpha into first column of A plus beta into second column of A plus up to, and if A is m into n, there will be n columns. So, eta no, it will be nu, right, no, eta into nth column of A, and each column is basically A11, A12, A1m is basically a vector containing each term in the row. So, if I can x is equal to b is solvable, then b must be in the subspace which is spanned by the columns of A, or b must lie in the column space of A. That is the importance of the definition of spanning. By getting column vectors, we will define a space which is spanned by the column vectors, and b must lie there for existence of the solution x is equal to b. If the columns are independent, then null space of A is equal to 0, and we have seen that column is independent means the solution. So, for example, I have a matrix A11, A12, A13, A21, A22, A23, A31, A32, A33, and x1, x2, x3 is equal to, this is the null space equation, if the columns are independent, then we can write x1 a11 a21 a31 plus x2 into a12 a22 a32 plus x3 into a13 a23 a33 is equal to 0 0 0 will imply this will imply that x1 x2 x3 is 0 0 0 or null space of A is 0. If the columns are independent, then null space of A is 0, and if the null space of A is equal to 0, the solution of unique, because we have again seen that solution can be divided as the null space solution, decomposed as null space solution and particular solution. The infinite solution, possibility of the infinite solution comes from the null space solution. If null space is 0 0 0 or null space is the equation is a trivial equation, then there is no infinite solution, there is a unique solution. So, independence is linear independence is involved in the definition, in the idea of uniqueness of the solution. That is, that if we have a linearly independent set of columns, then the solution is unique. If we have B vector which is lying in the subspace spanned by the column, then the solution exists. So, linear independence and spanning are in that way important in finding out existence and uniqueness of the solutions. Now, we come to the definition basis of a vector space. I have earlier seen that there are minimum number of vectors in any real coordinate space R which is needed to span over the entire real coordinate space R n, and there can be more vectors which are spanning over this space, but those vectors will be linearly dependent. Similarly, if we have that minimum number, but the vectors are linearly dependent, then that will not span the space R n. So, this gives the definition of basis of a vector space. Basis of for a vector space V is a sequence of vectors having these two properties once, that they should span, the vectors are linearly independent, the vectors will be linearly independent and they should span the entire space V. So, linearly independence means that they will be the minimum number of vectors spanning the space. If we add one more vector to that particular set which is spanning the space, that will be linearly dependent with previous vectors, because like for R3, 3 vectors are 1 0 0 0 1 0 0 0 1, these 3 vectors are needed to span the entire space. If I add another vector 1 2 3, that will be linearly dependent on these 3 vectors. So, for example, if we take the case of R3, we have spanning linearly independent vectors one 0 0 0 1 0 0 0 1. Now, if I add 1 2 3, this entire set will also span the space R3. However, 1 2 3 is linearly dependent on these vectors. So, this will not remain linearly independent, they will be linearly dependent set. So, minimum number of linearly independent vectors which can span a space is the basis of a vector space. Similarly, if we look into the other criteria or other property, that they will span the space, and this is the maximum number of linearly independent vectors which are spanning the space. If we have two linear independent vector in R3, they will not span the space. If we have we can have maximum 3 linearly independent vector in R3 and they will only span the space. So, if we add, if we take a space which is spanned the maximum number of linearly if we take a space which is spanned by two linearly independent vectors, that will not span the entire vector space unless this is the maximum number of linearly independent vector in that Rn. So, nevertheless the basis of a vector space will be a sequence of vectors, a set of vectors which will be linearly independent as well as they will span the space, and therefore, there has to be one particular number of vectors which will span the entire space and which will be linearly independent. There is another important property of a basis, and that any vector in a vector space is obtained by a unique combination of basis vectors. So, let us assume V1 to Vk are basis vectors in the space V. So, any vector V which belongs to this capital V vector space can be expressed as a linear combination of A1 to A1 V1 to K Vk. Now, let there be let us say that this statement is violated that there is another type of combination of vectors which can express V as B1 V1 to Bk Vk. Now, we will subtract 1 minus 2 and this. So, V1 to Vk is spanning the entire space V. So, any vector V must be expressed as linear combination of A1 to A1 V1 to AK Vk. Similarly, let us assume that there exists another linear combination of the same vectors which can express this vector. So, if we subtract 1 from 2, we get A1 minus B1 V1 to AK minus Bk, Vk is equal to 0. So, V1 to Vk are basis vectors, therefore, the basis vectors are spanning as well as linearly independent. They are linearly independent. If I say any combination of them is 0, that means all the coefficients must also be 0, else these vectors are linearly independent. A1 V1 to AK Vk is equal to 0. So, A1 is equal to B1 and AK is equal to Bk, this combination is unique, and we can think it in terms of the perceivable real coordinate spaces like in R2. If I have a vector 2 3 that can only be added by going 2 in the x direction and 3 in the y direction, this only can be obtained. There is no other combination of x and y through which we can obtain the vector 2 3. Similarly, we can think it in 3D also. So, there has to be one unique combination of basis vectors which is giving one particular vector in a vector space. There can be infinitely many bases of any vector space, like, so basis, I will probably clear this idea basis. Basis is plural of basis. If I can form one basis which combines n vector of a vector space Rn, n is of a real coordinate space Rn, I can, or any vector space, for any vector space V I can form one basis which has n vectors. I can form another basis with n vectors for the same vector space V, and these are very common examples which we already have encountered in different branches of study. For example, I j k vectors, one I direction, j direction and k direction, unit vector in each direction is a basis of R3. I can express any vector in a 3-dimensional real coordinate space by ai plus bj plus ck. Also, E theta is Er, E theta, Ez, which are polar coordinate unit vectors, are basis of R3. I can express same vector using polar coordinate. So, I can think of, I can express this is I, this is j and this is k. I can express any vector by ai plus bj plus ck. Similarly, I can think of the polar coordinate vector space, which is er, and then tangential to it e theta, and then Ez. So, I can express again this vector by alpha er plus beta e theta plus gamma Ez. So, they are linearly independent, separate linearly independent set which is spanning over the entire set R3. So, they are also both are bases. So, there are two bases which we can see. We can also get further more bases I plus j, for example, this one I plus j. So, this is I plus j and maybe this is I minus j and this is k. I plus j, I minus j, k, these also can form another basis, and so we can have any number of bases. We can think of basis like this, this vector and this vector. They will, any vector in R3 can be also expressed as linear combination of these vectors. So, any infinite number of bases is possible, infinite bases is possible. Each basis, so each is a basis, an infinite combination of vectors is possible, or infinite bases or bases are possible for one particular vector space. However, in R3 we can see any basis has 3 independent vectors. So, this number is fixed, that what is the number of vectors in a basis has to be fixed and they have to be linearly independent. Then they can span the entire space and they are also linearly independent. So, they can form a basis. There can be maximum 3 independent vectors in R3, seen it earlier. There can be minimum 3 vectors which span R3, that gives me rise to this number 3, which is needed for, which is a needed number of vectors in a base, in an R3 basis. There can be infinitely many bases. So, how can we have the base, does the basis of a subspace look like? For consider a matrix in the echelon form 1 0 0 1 3 3 2 0 0 1 1 0 0 0 0. So, this matrix, the column space has like the third column, second column is dependent on the first column, and the fourth column is also in a way dependent on, say, third column and first column, third column and first column. So, there are 2 independent columns which are the first column and third column, or first column, second column or fourth column. There can be maximum 2 independent columns in this vector, though all these columns are members of R3. So, we can write column space is a linear combination of alpha 1 0 0 and beta 2 1 0, and they are the basis. I can add another vector in, because this is the spanning of column space what I am discussing. I can add another vector, I can add gamma into 3 1 0, but 3 1 0 will not be a basis, it will have only 2 bases. So, what becomes an important idea is that this, though all these vectors like C1, C2, C3, C4, all they belong to real coordinate space of dimension 3, the column space, what is the column space look like? It is 1 0 0 2 1 0. So, the entire column space lie here. The column space is a plane, column space has one dimension less than the 3D space, though the vectors are member of 3 dimensional space. So, the column space has 2 basis vectors. Column space vector, all column space vectors will have the third component is equal to 0. So, column space does not span over the entire R3. if this is R3, all the column space vectors, this is how the column space look like. Column space vectors lie in one particular plane. So, this is a, what we will say, that column space is a 2D space in 3D real coordinate space. The main geometry is a 3D geometry, but the column space do not span over the entire geometry. Whatever is a column space vector is only restricted to a 2D geometry. So, what we are seeing, the dimension of the column space is not same as the dimension of the real coordinate space, and that will give rise to another definition. What is dimension? Dimension of a vector space. When we express a vector space by certain components, we say that this vector is a member of a real coordinate space of that dimension. However, vector space or a subspace is a part of that, like here we discussed about a 3D real coordinate space, all vectors are member of a 3D physical space, but the column space is not, all column space vectors are expressed in 3D coordinate terms. However, the column space is a 2-dimensional space, so it has a dimension less than 1. And what is important in column space, the 3D R3 has 3 basis vectors, but column space found only 2 basis vectors. So, number of the vectors in one base, in the basis, will tell us what is the dimension of the space. And we go to the definition. Dimension of a vector space. Any two bases for a vector space V contain the same number of vectors. We can have many basis vectors, but all bases should all the bases, any base there, in any basis there should be, all the bases rather, or in any basis there should be fixed number of vectors, and this number, which is shared by all bases, expresses the degree of freedom of the space. We say it column space is a 2-dimensional space, any vector in the column space must be within that 2-dimensional space, it cannot come out of that 2-dimensional space. So, it defines the degree of freedom of the space, and it is called the dimension of the vector space V. So, if we write V belongs to C1 V1 plus C2 V2 plus C3 V3 plus C4 V4, and V1 has, or V11, V12, V1 n, then dimension, then what is the dimension of the vector space V? It is not n, n is the component of vectors, components which is needed to define any vector that. So, n is the dimension, n is dimension of real coordinate space Rn, and 1, 2, 3, 4, 4 is dimension of V. The number of vectors that is needed, independent vectors that is needed to express or span over the entire space V, the number of vectors included in a basis of V is the dimension of V, and the number of components in any vector is dimension of the real coordinate space n. They are not necessarily same, there can be cases when they are same, when the vector space or the subspace spans over the entire real coordinate space, these dimensions are same. Otherwise, the dimension is always less than the dimension of the real coordinate space, because we have seen that if real coordinate space has a dimension n, there can be maximum n independent vectors. So, the number of vectors in a basis can be at most n, it can be less than that. And what is the number of vectors in the basis? That will tell us what is the dimension of the particular vector subspace, and the number of components in a vector will tell me what is the dimension of the real coordinate space, because we need that many vectors to form a basis of the real coordinate space. So, another important thing is that there can be many bases, and bases means sets of basis vectors. There can be many sets of basis vectors. Each set of basis vector is a set of linearly independent vectors which can span the entire vector space. However, each basis must have fixed same number of vectors, and this number is the dimension of the vector space. There can be many bases, many sets of basis vectors. However, each basis must have fixed number of vectors, and this number is the dimension of the vector space. That what is the number of vectors in one particular basis. If, and we have earlier said that if there are two bases, each of these bases will have same number of vectors. So, we think of basis with V1 to Vn where there are m basis vectors, and another basis with W1 to Wn where there are n basis vectors. So, we think that the statement is violated, and in matrix algebra we will several time do this what is called second law of thermodynamics type of proofs, that Clausius statement is violated and we will see whether Kelvin Planck statement holds. So, we will get one statement violated and we will see whether the proposition still holds, satisfies some other criteria. So, we will earlier said that all the bases will have same number of vectors. Now, we are telling that let us consider two bases of same vector space, but they have different number of vectors. But we will see that the number will be same. So, if these are different, m is equal to n, but we will try to prove it as m is not is equal to n and then see what is happening. So, intuitively what will happen, that linear independence will not be varied, but let us see. Suppose n is greater than m, w's are more than v's, there are more w's than v's, but they are basis of same vector space. As v's span the space, any vector in the same vector space can be expressed as combination of v's. So, w's and v's are also member of the vector space. A basis is also the member of the particular, it lies within the vector space, and combination of basis will span the entire space. So, V is one basis, all V's are from span the entire space. W's are also in the same space, they are also another basis, they are also in the same space. So, any W can be expressed as the linear combination of all the V's, and we will see that any W in the is a linear combination of V's. W1 is equal to A11 to V, combination of V's. Similarly, we can write W2 is linear combination of V's, Wn is linear combination of V's. So, we can now these W and V, they are vectors, they are in vectors in Rn or Rm wherever. So, they have m or n components in each. So, we can write each vector is as their vector, each vector W is respective column of the multiplication of V and W. So, this is a vector multiplied with another matrix. So, the product is another, this is a all these are vectors. So, product is a matrix where these are each column of the matrix. So, we get W is equal to V A. So, now this matrix A has n columns and m rows. A is an n into m, m row and n columns. So, A is an m into n matrix, m rows and n columns with n greater than m, fine. So, you get a rectangular matrix here, which multiplied with the vector combination of column vectors V gives me the combination of column vectors W, and V and W are the bases. As A is m into n matrix, A is m into n matrix, m rows and n columns with n greater than m, there are more variables than the number of equations. Their number of variables are more than the number of equations. So, null space is non-zero. So, solution of x is non-zero, x is non-zero as a solution of x is equal to 0, x non-zero is a solution of V A x is equal to 0, V A is equal to W. So, x non-zero is a solution of W x is equal to 0, and we will get W 1 x 1 to W n x n is equal to 0, and that will tell us that W's are not linearly independent and they cannot be a basis. However, if we start n greater than m, we arrive at a point where the vector one basis W does not remain linearly independent and they cannot be a basis. So, n greater than m is not possible because W's form a basis and that required that they are independent. So, n greater than m is not valid. Similarly, we can show that m greater than n is not valid, then V's will be linearly dependent. Therefore, m cannot be greater than n cannot be greater than m. So, if V and W both are bases, then the V has m vectors and W has n vectors, m must be equal to n. If we have a spanning set which is not a basis, a spanning set can have many vectors, it is not needed that all have to be linearly independent. Then, but there are minimum number of vectors which are linearly independent which will span the entire set. So, if we have a spanning set which does not have a base, which is not a basis, but a spanning set, we can reduce few vectors and get a basis. So, basis has minimum number of spanning vectors. Similarly, if we have a linearly independent set which is not a basis, that means it does not span over the entire set. So, you have to add few more linearly independent vectors and that will be a basis. So, again this tells us that basis has maximum number of linearly independent vectors, and this number, the minimum number of spanning vector, maximum number of linearly independent vector, this number is fixed and this is the number what is the number of vectors in basis, and we call it to be a dimension. So, number of vectors in a basis is a dimension, that is the maximum number of vectors which are linearly independent in that particular space, and this is the minimum number of vectors which can be used to span over the entire space. So, we finish the discussion on linear independence, spanning, basis, and finally, we get what is dimension of a vector space. Now, we will use this idea of dimension of a vector space in finding out dimension of column space, null space, row space. Another space we will discuss on row left null space and see how they will be important in finding out solution of A x is equal to b, in which we are focused now.